Okay, we're going to basically now look at some overview, essentially, what we've been talking about in Chapter 7 and really before that, and just how do we find antiderivatives? What are some strategies for integrating functions? And so really this is just a review of what we've already talked about. And so let's go sort of go in order of this. Number one is, can you do some obvious simplifications, or can you make things simpler? That's always a good idea. Is there any algebraic simplification you can make? Can you simplify a fractional expression by eliminating common factors in the numerator and denominator? Can you use trigonometric identities? Okay, so here's some quick examples. Look at the first one here. You might begin to think, wow, what am I going to do here? Try a substitution of u equals cosine x. I need my du to be negative sine x, and I don't see a sine x anywhere in here. But if you just look at this and realize, hey, there's a nice trig identity, right? Namely that secant x is equal to 1 divided by cosine of x, right? Reciprocal identity, right? And so 1 divided by cosine squared of x is what? Secant squared of x. So this just becomes the integral of 5 secant squared x. And then we realize, hey, I know the antiderivative of secant squared x is what? Tangent x. Because the derivative of tangent x is secant squared x. And so there's your answer. Right? So sometimes you might think it's very complicated, you start doing substitutions and other things, but try simplify first. May not always help, but a lot of times it will be helpful. Here's another example, Here you got a product, some of you might be thinking, hey, let's use integration by parts, right, when we have products of things. No. And some others will incorrectly say, well, let's just take the antiderivative of 3x minus 1, the antiderivative of x plus 4, and multiply those together. That won't work either, right? The integral of a product is not the product of the integrals. The obvious thing is to simplify by just expanding and combining like terms, right? FOIL this thing out, right? If I FOIL this thing out, 3x times x is 3x squared. The outer is 12x. The inner is negative x. 12x minus 1x. It's 11x. Last, negative 1 times 4, negative 4. Just multiply that thing out. And now it's just a simple, right? Using the sum difference rules, constant multiple rule, constant rule, power rule, and we're basically there, right? The first antiderivative is x cubed. Second one is 11 halves x squared, and then negative 4x. Okay, the next one again, you just can't take the antiderivative of the top and the antiderivative of the bottom and then divide those results. The integral of a quotient is not the quotient of the integrals. And, again, integration by parts, someone might say, well, no, that's not a really good choice either. Again, simplify, right? So remember, the square root of x is the same as x to the 1/2. And I can, notice since I have a monomial, a single term down here, I can divide each term by that. So this becomes x cubed divided by x to the 1/2 plus x divided by x to the 1/2 minus 1 divided by x to the 1/2. And simplifying these, what do? Subtract the exponents. I get x to the 3 minus 1/2 is 6 halves minus 1/2 is 5 halves, or 2.5. Plus 1 minus 1/2 is 1/2. And then this is what? 1 divided by x to the 1/2 is x to the negative 1/2. That's another important simplification we want to be able to do. Right? So this is now a function I'm integrating, and so very easy to get the antiderivative. This will be what? X to the 5 halves plus 1 is 7 halves, divided by 7 halves, or times 2/7. Antiderivative here is going to be what? 2/3 x to the 3/2. If I add 1 to a half, I get 3/2. And then here, adding 1 to negative 1/2 gives me positive 1/2. Dividing by positive 1/2 is the same as multiplying by 2. So a quick simplification could come in handy. So always try and simplify as best you can first. Combine like terms, etc., etc. After simplification, you know, our next most general and basic strategy is to use substitution, right? So see if a substitution would work. And you know, sometimes it does, sometimes it doesn't. Sometimes it requires a little extra work. So let's look at some of these. Here's a pretty easy one. Remember, what are we looking for typically? The typical substitution is to choose u to be the inner function of a composition. Not always. There's other types we've seen. So remember, anytime you use a substitution, we need to know what that du is, right? In this case, it's going to be 3x squared dx. And then I look, that's good in a sense because I've got an x squared dx, so I just need to look at 1/3 du being x squared dx. And so all this information tells me that this integral is 1/3 can come outside. The x squared dx is the du, the 1/3 du, and I got cosine of x cubed or cosine of u du. And so that integral now is easy to do. The antiderivative of cosine of u is sine of u, and then we go back to the original variable. Down here, in a similar manner, what would our substitution be? Probably 1 plus e to the x, right? That's inside the square root function. Notice in that case, my du is e to the x dx, and that's a good thing because what do I have? E to the x dx. So this one very easily becomes square root of u, or u to the 1/2, e to the x dx du. Easy to find the antiderivative, and of course we go back to the original variable, u being 1 plus e to the x. Oops, 2/3 there. Okay. Let's look at another example here. In this case, what would you let your u be? Well, we can try u is 1 plus x squared, right? That's under the radical. So du is 2x dx, right? Now when I look at this, I see an x cubed dx, right? An x cubed dx. Well, certainly I can look at 1/2 du being x dx. Now, if you say multiply both sides by x squared, which would give me my x cubed dx, you could do that. But what is x squared? Notice right here that if I subtract 1 here, x squared is equal to u minus 1. Right? And so that would be an important relationship. So if I multiply both sides of this by x squared, which gives me 1/2 x squared du equals what? X squared times x cubed dx, right? Here's my x cubed dx. I don't want to mix variables ever, so I don't want to have x's and u's together. I want this to be all in terms of u, but this is what I'm going to do, right? I'm going to replace x squared with that, and so this is 1/2 u minus 1 du is x cubed dx. So this requires a little extra step in the substitution. If you're going to substitute to a different variable, everything needs to change to that new variable. So the square root of u, that's u to the 1/2, and the x cubed dx is 1/2 u minus 1 du. Now this 1/2 can come out. And what do I have? Distributing u to the 1/2 through, I get u to the 1/2 times u is u to the 3/2. U half times 1 u to the 1/2 times 1. And now I can find the antiderivative. Seems like we've seen a lot of these before. This one will be what? U to the 5/2 divided by 5/2 or times 2/5. And then add 1 to that, 3/2 or 2/3 u to the 3/2. Distributing the 1/2 through and going back to my original variable. 1/2 times 2/5 is 1/5. One half times 2/3 is 1/3. And there's my result down there. Again, there are more than one way sometimes to do a substitution, so there's another way you could actually do the substitution. And I might have you play around and try this on your own. This substitution works fine, but you might want to try this substitution. Try w equaling the square root of 1 plus x squared. You say, well, how does that work? Well, before you take any derivative, square both sides. Right? And then if you take the derivative now, what's the derivative here? That's 2w dw over there, and here it's going to be what? Derivative of 1 is 0, derivative of x squared is 2x dx. And try and proceed from that standpoint, right? I'll let you finish that out and see if you can indeed, you try this. You've got this x cubed dx, and so how are you going to proceed with that? If you notice from this equation here, x squared is equal to what? W squared minus 1. And you need to get, x cubed here. So if I multiply both sides by x squared, I can divide by 2. So this thing becomes w x squared dw equals x cubed dx. Right? And then the x squared you want in terms of w here will be w squared minus 1. So try that and then show that you get back to the same thing. Okay, just a little aside there. Try some different things. Try that. That's a little different. So there's different ways substitution can work. It's not always let u be the inner function of composition, but a lot of times that works. Doesn't always work, but you need to try something and see if substitution works. Okay. Now, what else can we do if substitution? Oh, I want to do one more. Yeah, sorry. I want to do one more example. Forgot. Here it is. All right. How about this substitution here? Well, if I go along with using the inner function inside 1 over the square root of u, we've got the square root of x plus 1. We've got a square root inside a square root in a sense, right? Now, I'm going to play around with this a little bit differently in this case. Instead of taking the derivative, I'm going to solve for the square root of x first, which is u minus 1. And then if I square both sides, I get this. And this is kind of what I was showing you in that second substitution on the last problem. Okay? Doing it this way just makes life a little bit easier when you're taking the derivative, because when you take the derivative of x to the 1/2, you get 1/2 x to the negative 1/2. Just radicals are kind of messy. And I can do this and get rid of this and take the derivative now, right? So dx is what? What's the derivative here? Really chain rule technically, right? U plus u minus 1 squared is going to be 2 times u minus 1 to the first power times du, right? And if I go and look at this, and of course, how did I, another way of saying how do you get this expression? if x is equal to u minus 1, really this is dx du, the derivative of x with respect to u is 2u minus 1. And that then multiplying both sides by du gives me that, if you're trying to figure out where I got that from. Okay, so now when I go and change the variable, so let's change the variable here. I've got everything covered, right? What's the dx? The dx is 2u minus 1 du. Right? What's the denominator? Square root of what? U. So square root of u, or u to the 1/2 power. Okay. Clean this up. This 2 can come out, and I'm left with u minus 1 divided by u to the 1/2. So how am I going to do that? Simplify, right? I can simplify. I can divide both of these things by u to the 1/2. Right. Simplify, now simplify. Okay, and so we've done this before. Here I get u to the 1/2. Here I get u to the negative 1/2. And the antiderivative. Distribute that 2 and go back to the original variable. Remember, our original variable u was equal to what? Go all the way back. Square root of x plus 1. Two times 2 is 4/3. 2 times 2 is 4. And then square root of x plus 1, or to the 1/2 power. Okay. So that required a little bit extra work, if you will. Okay. So substitution is our main tool, and a lot of times we use substitution in different ways with other techniques, in combination with other techniques. And so, after we've sort of said, can we simplify, can we use substitution, what are some other things we've talked about? Well, certainly integration by parts, and if nothing else works, simple substitution doesn't work, and we've got a product or a quotient of functions, that's where we use the integration by parts. And remember, choosing this u right here, what's the u going to be? Remember our acronym we use, LIATE, right? So first choice would be any logarithmic function for u, then would be inverse trig function, then would be algebraic function. Way down the list is trig function and exponential function, right? That would be the last choice we would possibly make for u. Okay. So if we have a product or quotient, we choose u to be in this order. dv is everything else, and then we evaluate the integral using integration by parts. Integration by parts is also good, we saw, for evaluating the integrals of these functions, right? We say there's no product here. Well, there actually is. If you choose u to be natural log of x, dv is just dx. And you can proceed with that. And then there's also special ones, right, where we encountered something like this, e to the x sine of x dx. And that's one where we kind of, exponential and trig are the only choices for functions, so we're way down here. When we choose, u to be, for instance, sine of x, dv is e to the x dx, what happens is we go through 2 iterations of integration by parts, and we just get back to this original integral. We don't get anywhere, it seems like. However, once we get that other integral, we will have an equation, basically, to solve for that integral. And so we looked at those techniques. Some other special techniques, that come then, we talked about how to evaluate certain trig integrals, and there's lots of different ones we can look at, but integrals of this form, products of powers of sine and cosine, products of powers of tangent and secant, we talked about techniques for doing that, and so you want to review that. Trig substitution allowed us to evaluate integrals involving these forms, right, using these trig substitutions. Partial fraction decomposition for integrals involving ratios of polynomial functions. Might need to use polynomial long division. Right? So we have all these strategies and some very special case type strategies, special techniques. And then in the last video I talked about integral tables, right? And I did some examples there. I want to do one more example of an integral table. And just remind you, sorry, I've got to pull up my integral tables. Just remind you of the integral tables. Here's the ones from our book that we'll mainly be using, and we mainly looked at these forms here. A squared minus u squared under the radical, u squared minus a squared, and so on. And again, these forms can be calculated essentially using the trigonometric substitution. But there's other forms on here, ones involving products of inverse trig functions and so on and so forth. Lots of other, these are some of the, we proved some of these and looked at some of these when we were doing trig integrals, if you remember. Okay, so we're going to look through this list. There's some more here as well, and we're going to see what we come up with. Okay, so let's take a look at this example here. All right, so if I were, encountered with this integral here, what can I do? You say, well, I can let u be 1 plus e to the x, right? Maybe I get 1 over u du, like a simple natural log. The problem is du is what? E to the x dx. I don't have an e to the x up top, so it's not a simple substitution. It's not a simple substitution. Okay. However, notice that e to the x is what, if I subtract 1, is equal to u minus 1. And so, if I come over here, du is e to the x, which is u minus 1 dx. Now, I don't like my dx's to be with my u's, so if I divide by u minus 1, I get my dx. Now, what does this do? So if I use this particular substitution, right, what do we get? Dx is what? Du divided by u minus 1. That's what I have up top. And down below I have 1 plus e to the x is just u. Right? Well, simplify, right? Simplify. How does that simplify? Well, if you're dividing by u, that's the same as multiplying this by 1 over u, and this becomes du over u times u minus 1. Okay. Now, this form could now be done using what? Could use what? Partial fraction decomposition. Partial fraction decomposition. But I'm actually going to use the integral tables this time, and to do that I'm going to make a slight adjustment to what this looks like. I'm going to write this as u times negative 1 plus u. Is that the same as u minus 1, negative 1 plus u? Yeah. Okay. So you could use partial fraction decomposition, but if you look in the table, look at these forms, a plus bu forms, and that's really what we have, a plus bu, or in this case 1u. But take a look at this, number 95, u times a plus bu. U times a, what's a going to be? Negative 1, plus bu, what's b going to be? 1. So this is also number 95 with a equal to negative 1 and b equal to positive 1. Okay. So So I'm going to make use of that. I'm going to make use of number 95. Which, where did this 95 come from? It came from partial fraction decomposition. So you could use partial fraction decomposition. So it's going to be 1 over a natural log u divided by a plus bu, absolute value plus c. Right? Again, by number 95, we have it's 1 over a, and what was a equal to? -1. Natural log, absolute value, of u over a, which is -1 plus bu. That's -1 plus u. So I was just, again, using the integral tables, I was just exactly using number 95 and just plugging in these values with a equal to 1 and b equal to -1. Okay. Now, of course, I'm going to go back and write this as u minus 1, same thing, u minus 1, because I want to go back to the original variable, and notice what I have here. I have negative, right, 1 divided by -1 is negative, natural log, and u, what was u? 1 plus e to the x, divided by, what's u minus 1 going to be? U minus 1. Well, if u is 1 plus e to the x, if I subtract 1 from both sides, what do I just get? E to the x, right? U minus 1 is e to the x. You might ask, hey, what happened to your absolute value bars? Yeah, I could put them there, but notice e to the x is always a positive quantity. Always a positive quantity. So this expression is always positive, so I don't really care about the absolute value bars in there. Okay. Now, here's the answer, and that's fine, but there are other forms, again, that you can put it in just to remind you of that, using the properties of logarithms and other things there. Notice this -1 can be coming up as a -1 exponent, so this becomes natural log 1 plus e to the x over e to the x to the -1, which is the natural log of what? The -1 is the reciprocal. Guess I need a plus c in here in each of these cases, right? But I can also even simplify more, because the natural log of a quotient is the difference of the natural logs. This is natural log of e to the x minus natural log of 1 plus e to the x plus c. And what is the natural log of e to the x? It's just x. And so another possible answer that we can write is the same thing, is x minus the natural log of 1 plus e to the x plus c. And not a space there. So again, the idea is, when you're finding antiderivatives, you might come up with an expression. If you're using another computer algebra system, another symbolic integrator that can do the integration, it might come up with an answer that looks slightly different, especially when you have expressions involving logarithms or trig functions. Okay? All right, so that's just an overview again, reminding you we have many strategies available that we've learned for finding an antiderivative. Now, so if we're evaluating a definite integral, and we haven't evaluated too many definite integrals, but if we're doing a definite integral, then we have all these techniques to find the antiderivative, right? Because then we can use the fundamental theorem of calculus, assuming we have a proper definite integral. What happens, though, if all these techniques fail and we're trying to evaluate a definite integral? Do we have any recourse? Do we have any way of evaluating a definite integral? The answer is yeah. If you go back to the beginning, we used rectangles, if you remember, to approximate the value of the definite integral. we are going to, in the next lecture, talk about numerical methods for evaluating definite integrals.